I'm going to talk about the general structure of the trace formula. And this is a subject that attracted a lot of attention in this community, well, since the time of Gutzwiller, but very intensive activity from the mid-1980s to the mid-1990s, by which stage a good deal of understanding had been reached about how the trace formula works. And subsequent to that, there have been many applications of those insights that were gained in that time, and I'd say not a lot of fundamental thinking about the general structure of the trace formula, sort of gross level. So why return to this? Well, I think that I at least missed something, and I want to tell you what it is I missed, and I'm not aware of other people having seen this as well, but perhaps people will tell me that I should have read their papers 30 years ago much more carefully than I did. I'm going to use the blackboard, because they are rather splendid and someone should use them, but I'm a little daunted by the size of the chalk. So if my handwriting is too large scale, do let me know. So we're going to start with quantum Hamiltonian, which we'll imagine has a chaotic classical limit. And the trace formula, as you'll know, concerns the determinant of E minus H, and in particular the log of that. And the idea is that semi-classically, as H bar tends to 0, you can represent the log of the determinant suitably regularized over periodic orbits. And so, as I say, a lot of energy was put over many years into understanding how the orbits contribute, what the relations between different contributions are, and that's going to be the subject of this lecture. So we look at the log of the determinant. The imaginary part of this, it's a complex number. The imaginary part of this is just gives you the counting function for the eigenvalues. So the staircase that increases with a jump of height 1 at each eigenvalue as E increases. And the real part of the logarithm tells you something else about the size of this determinant. And we understand, again, one of the achievements of this community has been to understand that you can model statistical quantities, for example, the statistics of the log of the determinant, using random matrices by averaging over random matrices from some appropriate ensemble. And just for definiteness, this lecture, I'll imagine that this Hamiltonian has no time reversal symmetry. Absolutely not necessary that I assume that, but it just will make things a little more concrete. And so if we assume that, we might expect that the statistical behavior of the log of the determinant is the same as that of the log of the characteristic polynomials of random matrices, and that leads you to a prediction that the log of the determinant, if you normalize by the square root of a half log th over t0, where th is the Heisenberg time conjugate to the mean level separation, and t0 is any canonical classical short time scale, for example, the length of the shortest periodic orbit. The idea is this will converge to a complex normal random variable with mean 0 and variance 1 in the limit as h bar tends to 0. So there's a central limit theorem for the log of the determinant, and that tells us something about what the log of the determinant looks like. So if I plot the real part of the log, it's a function which has singularities, logarithmic singularities at the energy levels. Etc. And it tells you that this function, when appropriately normalized, has a logarithmic value, has a Gaussian value distribution, and the same for the imaginary part. What I want to think about are not the statistical properties of this, or I will return to that later, but exactly how the periodic orbits contribute to sums of this form. And to do this, I want to imagine looking over a short energy window. So let's look at the logarithm of the determinant of E plus epsilon minus H. Epsilon will be an energy window. So semi-classically, this is going to look like a sum over periodic orbits. P I over H bar is the action, plus I times the small energy over H bar times the period of the orbit. And I'm going to imagine this small energy window to be of some fixed size. So it's a window in energy starting at E, going up to E plus epsilon 0, and the number of energy levels in that range will be something like epsilon 0 times the mean level density. So what I want to imagine doing is the following. I want to imagine splitting this sum up in the following way. This is simply splitting the sum up into dyadic intervals in the periods of the orbits. So we go from the period of the shortest orbit up to twice that period, and then from twice the period to 4 times the period of the shortest orbit, from 4 times that period to 8, etc. Now there's nothing special about 2 here. I could choose 3. I could choose any other natural number. I could choose an unnatural number. You'll see a little later that there's nothing special about that. I'm choosing this simply for the purposes of illustration. To call this sum here, the dyadic sum inside there, to call this y k of E and epsilon. To construct the full periodic orbit sum, we have to sum over the yks. And if you want to evaluate the log of the determinant at some position in the window, epsilon 0, this tells you how to do that. You sum all these contributions. Here's your epsilon 0, and you're summing the contributions that depend on epsilon 0 and where the window starts. That's on the energy E. And so the question is how these quantities yk, what they look like. I should perhaps comment here on K's. We've understood from orbits, to all intents and purposes, can be truncated at the Heisenberg time, and max will satisfy something like 2 to the power k plus 1 times t0. This is the maximum period that appears is the Heisenberg time, oops, Kmax. And so Kmax is something like log to the base 2 of the Heisenberg time over any characteristic short classical time. So I want to analyze and think about how these functions behave. So the first thing to ask is, what's their average? For example, with respect to E, average through the spectrum. And it's not difficult to convince yourself that the contributions here are all oscillatory. You're averaging over these oscillations. This is going to be essentially 0. So the average of the y's is 0. What about variance? Well, just to make this a little clearer, to save any confusion arising, what I'm going to do is now specialize and look at the real part of the log. I could do this for the imaginary part of the log, and I could do it for the real and imaginary part together, but it's make the explanation a little simpler if I focus on just the real part. So then we understand how to compute sums like this. This is the sort of periodic orbit calculation that started in the early 1980s with the work of John Hannay and Alfredo Almeida and Michael Berry. We're going to use the diagonal approximation. So the average of the squares of the yks is going to be something like a half times the sum Tp between T0 2 to the k and T0 2 to the k plus 1 AP squared. And using the sum rule that John Hannay and Alfredo derived, this is something like the half the integral from T0 2 to the k, T0 to the k plus 1, dt over t, which is a half log 2. So that's the variance of these quantities. They have a variance that's fixed, doesn't depend on the mg or any other parameter. And if you compute the higher moments, again, within the diagonal approximation, it's no surprise at all. This is basically a random phase approximation, and so it's no surprise that these moments are all Gaussian. And so the expectation is that the yks converge to normal random variables with mean 0 and variance a half log 2. So that's how you should think of these yks. They're Gaussian random. They behave like Gaussian random variables with 0 mean, a fixed variance. And now if you add all of those Gaussian random variables together from k0 to k max, you reproduce the central limit theorem that you get from prediction of random matrix theory, and this would be the usual kind of derivation of random matrix theory using semi-classics. So I'm saying nothing terribly new here. But what I want to now think about is if these yks are Gaussian random variables, what's their covariance structure? So I want to consider what about averages of, say, yk, e epsilon, yk prime, e epsilon prime. So what can one say about the covariance of the y variables? Well, if k is not equal to k prime, these are sums of completely disjoint sets of periodic orbits. Because by construction, the periods of the orbits that contribute here are absolutely distinct from the periods of the orbits that contribute here. And so if k is not equal to k prime, this is 0. What about if k is equal to k prime? Well, again, within the diagonal approximation, this would be a half sum Tp lying between T0 2 to the k and T0 2 to the k plus 1 of AP squared e to the I over h bar Tp times the modulus of epsilon minus epsilon prime, for example, the real part of that. And using the Haney-Osorio sum rule, you can replace this by an integral. It's an integral from T0 2 to the k, T0 2 to the k plus 1, dt over t, e to the I over h bar, t modulus epsilon minus epsilon prime. And this is an integral that one recognizes straight away, and the asymptotics can be evaluated. And so this is the key point. This is half log 2 if the exponent here is small. So if modulus epsilon minus epsilon prime over h bar times T0 2 to the k is very much less than 1, and it's going to be essentially 0 if this quantity is very much greater than 1. And this is the key point. Now, this is a very trivial calculation, as you're seeing, but the conclusions that follow from this I think are really pretty interesting. So what do we learn? Well, if we want to get something non-zero, this condition has to hold. Let me write this out again. So we can think of this in two ways. One, as the energy varies, epsilon minus epsilon prime, as these 2 points within the energy window get further apart, or for fixed k, or we can think of this when the energy separation is fixed as k varies. So this is, I'm saying, I'm going to do a bit of trivial arithmetic here, which I'll almost certainly get wrong, but the implications are twofold. This means that if we think of k as fixed, to get something non-zero, to get a correlator that's non-zero, we need to be, for these energies to be quite close to each other. In fact, we need them to be exponentially close in k. So the larger the value of k, the closer these two energies have to be to get something non-zero. Alternatively, if we think of the energy separation as fixed, and we think of varying k, this becomes a condition on k, so basically that k has to be very much less than log to the base 2 of h bar over T0 modulus epsilon minus epsilon prime. And so this means that if we think of a fixed energy separation, it's only small values of k that are correlated. So we have, if you put these two pictures together, you come up with the following picture for how the periodic orbits contribute within the trace formula. And it looks as follows. And I think this is going to be the sort of key picture of this talk. And as I say, this is all a very trivial calculation. I've done the whole calculation for you on the board. But I think the picture is one that I didn't understand, and which now is being appreciated, has some interesting implications. So you should imagine this as a binary tree. Etc. Let me stop at this level. So this is my epsilon. This. Actually, I will put one more level in, just to make this a little clearer. So the way the periodic orbit formula works, the trace formula works as follows. If you want to evaluate the trace formula at some energy epsilon within the window that you're looking, you have to sum the contributions from the various yks that contribute to the value of epsilon. So you start at the top of the tree, and then you think, what's the unique path that gets you down to the value of epsilon? Different color. So for that value of epsilon, there's a y0, there's a y1. I'll just write epsilon here. I'll suppress the e. There's a y2, and there's a y3. And that's how the periodic orbit formula is structured for that value of epsilon. But what these two conditions above suggest is if you pick a different value of epsilon, your epsilon prime, well, you have to sum all the contributions that contribute to that value of epsilon prime. Well, the first one's in common. This is the statement that for small values of k, you have complete correlation within the sum. So the condition is that for small values, the second condition there, if epsilon and epsilon prime are fixed, for small values of k, things are completely correlated. So this is precisely y0 of epsilon prime. And this is precisely y1, and these are equal to each other. And this is precisely equal to y1 of epsilon prime. But at this stage of the tree, the two separate. So this is y2 of epsilon prime, y3 of epsilon prime, and those are different, completely decorrelated from the corresponding y's that contribute to epsilon. So there's this hierarchical tree-like structure underpinning the trace formula, which is a simple consequence of this very straightforward calculation of the correlations between the dyadic contributions within the periodic orbit sum. Now, why am I telling you all of this? Well, it turns out that this structure leads to new insights into how the statistics of the log of the determinant behave. Why? Well, I've told you that the y's, if you individually, behave like normal random variables. So they satisfy the limit theorem. So you should think of this in the following way, that if I want to pick my epsilon, my energy, and evaluate the trace formula there, it's a sum of Gaussian random variables. But if I want to evaluate it at some different energy, epsilon prime, that's also a sum of Gaussian random variables, but they're correlated in the way governed by this tree. They're correlated in the sense that the first few are exactly correlated, and then they exactly decouple become decorrelated. So this maps the problem, this formula, precisely onto a problem that's very famous in probability theory. It's called the branching random walk. And the branching random walk is a problem which is the precise embodiment of what I said. In the branching random walk, these will be not just semi-classically, they'd be taken to be precisely IID random variables, which are correlated if they have a common edge and completely decorrelated on different edges. And this is a hugely studied problem in probability, and it's realized that the branching random walk has some very interesting features which distinguish it from a simple Gaussian random function. So at any epsilon, if I choose my energy, the trace formula is a sum of, semi-classically at least, is a sum of Gaussian random variables. So it is itself a Gaussian random variable, and that's simply the central limit theorem that I wrote there. So the central limit theorem that is in the center of that board is nothing more than a statement that the functions that live on the edges of this tree are Gaussian random variables, and we're summing over them. But the fact that they have these correlations between different values that's governed by this hierarchical structure, it's understood in the theory of the branching random walk, has consequences for the sorts of questions that are precisely the questions that Sandra Paredo and Lev Kaplan were just describing to us. So if you look not at the typical values, but at the, what am I learned to call them, the super extreme values, the rogue values. So we're to look at the rogue values of the log of the determinant . And by rogue, I mean we ask, what's the very largest that this can be within the energy window that we're looking in? If this was simply modeled by a Gaussian random function, so if we were simply saying, let's ignore the correlations and simply model this as a Gaussian random variable at these points, completely decorrelated with values at any other point, the maximum of this would be something asymptotically that goes like log of th over t0 minus a quarter log th over t0 plus some random variable xe, which is of order 1 in probability. So it has some limited distribution, which is well known in the theory of extreme value statistics. It's called the Gumbel distribution. And these were studied in the 1940s and 50s by many people, Gumbel, Fisher. It's a famous problem to look at the extreme values, the rogue values, super extreme values, of independent Gaussian random variables. So what's the question is, having modeled this as a branching random walk, what are the consequences of that? Well, the consequence is that this asymptotic isn't right. So you would be led to this prediction if you simply said, well, I know the log of the determinant has a Gaussian limit distribution. Let's take its values at different points to be uncorrelated with each other. That would be the prediction you'd be led to. But it's not right. And in fact, the correct formula has a 3 there. And this is a well-known result in the theory of the branching random walk. And it would be what you would be led to if this semi-classical picture that I've sketched for you is accurate. So there are definite predictions that come from this, and this is very consistent with the sorts of message, the take message that Sandra and Lev were explaining, which is that if you simply model things as Gaussian and ignore correlations, you lead to predictions. But correlations, in this case, the subtle correlations that follow as a consequence of this tree-like hierarchical structure, really do affect extreme values. They don't affect the typical values, but they affect the extreme values. And here the consequence is that the asymptotic formula has to be augmented with this extra factor of 3. Now, what's the evidence that this is correct? Well, I don't know this picture's been checked semi-classically for any system, and it would be interesting to do that, I think. But of course, a natural thing to try would be to say, well, is this true within random matrix theory? So can one prove this sort of picture for random matrices? And the answer is yes. In fact, this was the random matrix calculation which motivated me to explain this in the context of semi-classical approximations, trace formula. But if we take U to be an n by n unitary matrix and look at the log of the modulus of the determinant of I minus u e to the minus I theta, then it's well known within this community, we could view U as a quantum map, that there is an expansion of this as a Fourier series, where the Fourier coefficients are the traces of powers of the matrix U, and you can play the same game. You can imagine splitting this up into intervals, etc. And if we call quantity here yk of u and theta, then the correlation structure that I've outlined to you, so in particular this correlation property between the yks, is actually a theorem. So it's something you can prove within random matrix theory, where the average there, of course, is an average over the CUE of random matrices. So this hierarchical tree-like structure is true within random matrix theory. And moreover, this sort of asymptotic for the maximum of the log, the rogue values, as I've come to love to call them, is the theorem. So that's a theorem, and that is a theorem with this factor of 3. So this factor of 3 exists. These correlations that are the consequence of the tree-like structure that I've tried to explain to you are real, they're manifest, and you can check them and they can be proved. So I think that gives one some confidence that semi-classically this will be true as well, and that semi-classically something like this hierarchical structure will be important in semi-classical sums. So let me just finish by setting this in a slightly wider, even wider context, because this connects something that we've all thought about for many years, the logs of determinants, so logs of resolvents, if you like, integrals of resolvents, or green functions, sets this in a slightly wider context, because it turns out that an even wider context for this. Where does the branching random walk come from? Well, there's a very wide class of problems that probabilists and high-energy physicists have thought about for some years, and these are what you might call log-correlated Gaussian random surfaces. So these would be a random surface. Think of a two-dimensional surface, which is random, and in fact it doesn't really exist as a function. It exists as a distribution. It's very wildly, think of it as very wildly fluctuating, so wildly that it fluctuating that it has to be thought of as a distribution and not actually as a surface. But these are very well studied by probabilists who've put this on a rigorous footing, by high-energy physicists, because these appear in many contexts in probability and high-energy physics, and you can think of them as two-dimensional analogues of Brownian motion. Brownian motion's a one-dimensional path that's so irregular one has to think of it in a distributional sense, and these are two-dimensional surfaces which are the natural generalization of that. And these appear in many areas. So one area that I'll finish with is that these are models of that appear very naturally in quantum gravity. So these are the kinds of surfaces that appear in Liouville quantum gravity, where they're called the Gaussian field. So you can this tells us that you can think of the problems that we've been studying, characteristic spectral statistics or statistics of these spectral determinants, as a bit like taking a slice through the two-dimensional Gaussian free field. And I think that's a point of view that I'm finding quite interesting. Thank you.
So, questions?
To the first part of your talk, you could also look at the quantum graphs where the semi-classical approximation is not